So today we'll begin chapter 2, resistive circuit analysis. And again, this is for some of you, if you hadn't taken physics a really long time ago, material might still be fresh. So consider it kind of like a review. Okay, there we are, right? Chapter 2, resistive circuit analysis. This is actually the bulk of our course. All of the circuit analysis techniques that we will review and the new ones that we will learn are part of chapter 2. Okay, so in some ways, chapter 2 is kind of the most important. Most of the topics on your final exam are also from chapter 2. Okay. Okay. All right. All right. First up is resistors in series, and then next up would be resistors in parallel. So this entire chapter is devoted to resistive circuit analysis. We're going to learn how to analyze circuits that are built with resistors. So if you have resistors connected in series, resistors connected in parallel, mathematically, we can reduce these connections down to one single equivalent resistance. Okay. So mathematical reduction to one single resistance. And we call that, or we label that as equivalent resistance because it is equivalent to a larger network of resistors. And hence the name REQ. Sometimes you might also see the term RT, where RT stands for R total. But more common is REQ. And REQ is what I use and what you will see in most of it. Okay. Now, important thing to keep in mind is that REQ is from the perspective of any 2 points in a circuit. So if there are, let's say there are 10 different points in a circuit, and you try to measure the resistance or REQ from, let's say, between A and B, you would get one value. If you try to measure it from the perspective of C and D, you would get a different value. The reason for that is, of course, the current that is flowing through each one of these resistors is different. So the voltage drop that occurs across each one of these resistors would be different. So REQ will change depending on the perspective. If the measurement terminals are different, then REQ will also be different. Okay. So if you take this simple series circuit, we have current I that enters the terminals, and current I goes to each one of these resistors. There's no other place for the current to flow through. So let's assume that there might have been a power supply connected to the left of these three resistors. If we wish to find REQ for the circuit, we are looking at it from the perspective of the source. Then we remove the source from our analysis. So it leaves behind open terminals. And these open terminals are where we are measuring the total equivalent resistance, REQ. And there is a small definition, derivation that we can go through where we apply KVL Ohm's law, and you find the voltage drop across each resistor. We have V1, V2, and V3. You apply KVL, the total sum of the voltages would be V1 plus V2 plus V3 is equal to supply voltage. Current I is common, you take it out, and what you're left with is Req equals the sum of the three resistors. Okay. So I won't do the complete derivation, but I can point out that the derivation comes from Ohm's law and KVL. Okay, yes. So question being asked is, does voltage always go from plus to minus? Excellent question. Okay. So let's take a slight detour. In a circuit, for a source, current always goes from minus to plus. Okay, from minus to plus. That indicates that it is supplying energy. It is supplying power because it's a source. So current always goes from minus to plus. For all other components, current always goes from plus to minus. Actually, all components that we are studying, resistor, inductor, and capacitor, current always flows from high to low. From plus to minus. Plus indicates higher end of the voltage. So current for a resistor always goes from plus to minus, high to low. The flip side of that is that if you have, so excuse me, the current always goes from high to low. So if you have a current flowing from left to right, then the voltage polarity is plus on the left, minus on the right. The voltage polarity is minus on the left and plus on the right, current's flowing in the opposite direction. Okay, so that would be the flip side. Current is like any other physical quantity, it always flows from high to low. Water or any fluid, due to gravity, flows from high to low. Temperature always flows from high temperature areas to low temperature areas. Pressure always flows from high to low. Current also always flows high to low. Okay, except when it's a source. For a source, it goes from minus to plus. Okay, so for a series circuit, you could have multiple resistors in series as long as there is a series connection between two of the resistors and that connection is unbroken. And the outer end of that connection, whether it's a 3 resistor circuit or whether it's a 300,000 or 3 million resistors in series, the answer for Req is that it is simply the sum of all 3 resistors in that circuit, or all of the resistors in that circuit. You could have 1,000,000 resistors in that series circuit. Sum of the 1,000,000 resistors would give you Req. Okay. So resistors in series are very easy to combine mathematically. Okay. Important point to note, current through a series connection always remains the same. There is no other pathway for the current to go through, so current always stays the same for all components. When we state that it's the same for all the components, it doesn't mean that it's going to remain constant. The point of this statement is that the current that results because of a series connection of resistors is a result of all of those resistors working together. So it's shared amongst all of them. If you have 3 resistors, 100 ohms each, and you apply a voltage of 300 volts, you would expect a current of 1 amp flowing through it. But 1 amp for all 3 of them. So the value for all 3 currents is the same. All 3 resistors is the same because they are sharing it together. If one of those resistors changes in value, then the value of the current will change, but it'll remain the same for all 3 resistors. Let's take a pause, think over that. Let me know if you have any questions. Okay. So current remains the same. However, voltage is divided. Whatever total voltage we apply is divided across each one of those resistors. And we will look at that in voltage division. For now, let's look at a simple example. Yeah, thought I did have. Okay, let's go back here. Okay, let's do resistors in parallel. So resistors in parallel, again, there is a small derivation or Req, and the derivation is based on Ohm's law and KCL. Okay, you have current coming through, that current gets divided. Each of those currents cause a voltage drop to appear across each one of those resistors, but because they are between the same nodes, voltage for those resistors is the same, current is divided, and you end up with an equation for Req that looks like this. 1 over R1 plus 1 over R2 plus 1 over R3 and the reciprocal. This 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3. And therefore Req is the reciprocal of the sum of the reciprocals. Okay. For a parallel network, again, equation does not, the equation remains the same, whether it's 2 resistors in parallel or 3 million resistors in parallel, as long as they're all in parallel, unbroken chain, the Req can be determined using these equations, right? In a parallel network of resistors, the voltage remains the same. And current is divided. And the point here again being that the voltage that appears across that parallel network is a result of all of those resistors working together. The cumulative combined effect. Plus, it's the same 2 nodes. Voltage is defined as the difference in electric potential between those 2 points. There are only 2 points or 2 nodes in a parallel circuit. There's 1 node at the top, there's 1 node at the bottom. There's only 2 nodes. If you measure the voltage between those 2 nodes, whether it's at resistor number 1 whether it's resistor number 10,000 or resistor number 1 million, it's still the exact same two nodes. Voltage will be the same. If any one of those values changes, then the voltage would change, but it will still be the same for all. Okay. All right. Any questions? All right. Two more things I'd like to point out. If you take a series resistive network, let's say you're adding 5 plus 4 plus 3. What is the answer for 5 plus 4 plus 3? 12. So you got 3, 4, 5, and 12. The REQ for a series network will always be larger than the largest resistor in that series network. It's 3, 4, 5. 5 is the largest. Your answer 12 is larger than 5. Our brains don't have to think about it. We automatically know if you add something to something, magnitude will always be larger. In a parallel network, it's the exact opposite. In a parallel network, the REQ is always, always, always smaller than the smallest resistance in that parallel network. So if you add 3, 4, and 5 in parallel, and you're trying to find REQ, the answer cannot be more than 3. It cannot be 3. It has to be less than 3. So in a parallel network, the REQ is always smaller than the smallest resistor. That's an instant verification. If you're trying to solve a circuit, trying to find REQ in a small part that is parallel, if your REQ is larger than the smallest resistor, then there's an error in your calculation somewhere. That's an instant verification check. Okay. REQ of a parallel network is always smaller than the smallest resistor in that circuit. Also, REQ of two resistors in parallel, let's say R1 and R2, is simply given by the product of the two divided by the sum of the two. So R1 times R2 divided by R1 plus 2. Yes. Question being asked is, if we had 3 resistors in parallel, could we do this twice? The answer is yes. Yeah. Technically, we could reduce 2 of those 3 resistors into one REQ, and then it's again in parallel with the third one, so you can apply it again, yes. But with powerful calculators at our disposal, at our fingertips, it's very easy to just calculate it out. And one final or third tip is this. If you have n number of resistors of the same value, R, then REQ is simply R divided by N. If you have two 10-ohm resistors in parallel, the answer is REQ is 5. If you have 3 in parallel, the answer is 3.333. If you have 50 1 kilo ohm resistors in parallel, 1000 divided by 50. So if it's all the same values, you simply divide the value by the number of resistors, R divided by N. And this is true only for parallel networks. Okay. For series, the equivalent would be same number of resistors in series, it's simply N times R multiplied by R. Right? 10 ohm resistors, you have 10, well, actually, you have 5 10 ohm resistors in series. The answer is 5 times 10 is 50. in parallel, it's divided by the number of resistors. Okay, let's look at the examples next. So here we have 4 circuits. We are asked to find Req from the perspective of the terminals on the left. Okay, Req from the left. So when you're trying to find Req, there are multiple techniques. One of the first and the easiest technique is when you have a circuit that is laid out in nice rectangular format like this. And what you do in that case is you start at the farthest end and you start reducing and you move towards your terminals of analysis, towards Req. So you start at the farthest end, you start reducing away from your terminals, and then you move closer step by step towards the terminals of analysis. So in this case, if I start at the far end, I can write Req is R4 in parallel with R3. The 2 slanted horizontal lines, or the 2 forward slashes in parallel, is my symbol for parallel. So R4 in parallel with R3, which is parallel with R2. And then those are in series with R1. Okay. And I will draw it out in a step-by-step manner. At least for the first one, I will. Okay. So you have this resistor right here. Let me call this R5. R5 is the parallel combination of R4 and R3. And this is R2. This is R1. Now, physically, these resistors are separate components. This is simply a mathematical simplification. Okay? This is simply a mathematical simplification to arrive at the cumulative effect of all these 4 resistors between those 2 terminals. This is R1. Let me call this R6. R6 would be R2 in parallel with R5. So I have 3 resistors in parallel. I have R4. R4 is in parallel with R3. I reduce that. I'm calling that as R5. R5 is then in parallel with R2. Reduce that mathematically to give me R6. Now, when I reduce it to R6, I can see that R6 and R1 are connected only at this junction right here. This junction, there's only 2 components. And because there's only 2 connections or 2 resistors, we can say both R1 and R6 are in series. Okay. Even though when we look at the circuit, it seems as if this is not in series. The cumulative effect is that at some point when we mathematically reduce the 3 resistors into one single resistance, then we can say that those resistors are in series, even though physically it does not seem as if they are in series. This is a very important point. It's important that everyone understands these concepts. Let's take a pause. Think over that. Let me know if you have any questions. Any questions? Good. Okay. Then I'd like to talk about a technique that may help you solve slightly more complicated circuits. And let's use that for B. And you're going to need this for one of the homework problems. So, example B, I'm going to label this node as A, this as B, trying to find REQ between these two terminals. Okay. If I'm trying to do this, in this technique, what you're going to do is you draw your terminals of analysis as two horizontal lines spaced far apart. Actually, instead of A and B, let me use X and Y. X and Y. Sub question is already labeled as A and B. So I'm trying to measure the REQ between X and Y. So in this technique, the goal is you have two horizontal lines. Those two horizontal lines are spaced far apart, and you're trying to get from X to Y, and you're going to place each one of the resistors in a vertical fashion. So between X and Y, I have R1 connected at X. So I'm going to draw out R1. Okay, the goal is to get from one terminal and reach the other terminal. So get from X to Y. So I look at R1. R1 is connected to X. And then the other end of R1 is connected to Y. So I can just draw a straight line down there. So far, so good. What else is connected to R1? Sorry, what else is connected to X? R2. So some distance away, I'm going to draw R2. Now, does R2 go to terminal Y? No. So we go to the other end of R2 and then look. What else is connected at the other end of R2? We have R3 and we have R4. So we have two resistors connected to the other end of R2. So I'm going to split this out into two. I'll draw those resistors, R3 and R4. And then where are those resistors going? We're going to terminal Y. So it's going to Y. That is also going to Y. So I'm simply going to drop a line like this, drop a line like this. Then I count back, look at all the resistors. I got 1, 2, 3, and 4. All of them are accounted for. And I have my circuit. All I have to do at this point is reduce each individual branch that I have here in this diagram to one single resistance, and then find REQ. So then I have this branch, and I have this branch. Does this technique make sense? Let me know if you have any questions. So what's the answer here for REQ? REQ is measured between X and Y, and I can see that R1 is one branch of the circuit, and it's parallel with the other branch of the circuit. And in that branch, I have, well, let's start with R3 and R4 in parallel first. And then they are in series with R2. Okay, R3 and R4 are in parallel, and thus they're in series with R2. And then, of course, the entire branch is in parallel with 1. And this technique will work on most circuits. Okay, it'll work on most circuits. Let's quickly talk about C and D. Start at the farthest end. R3 and R4 are in parallel. R1 and R2 are in parallel. And so my circuit can reduce to 2 resistors in series. This is R3 parallel R4. And this one is R1 parallel R2. And D is rather straightforward. You have REQ is equal to R3 in parallel with R1 and R2 in series. You can solve all 4 of these circuits using the technique I showed on the right for B, right here. And then if you can just practice it, and then let me know if you run into any issues or any questions. All right, we'll end class here today. We'll pick up here again on Wednesday. Keep up with the homework. The next homework due is based on REQ and then series parallel analysis.